Hi, I'm Willow Chandarina, Product Manager with the Amazon Elastic File System team. Today I'm going to be talking about persistent storage for containers running an Elastic Kubernetes service. We're going to start by talking about when and why you might want to use persistent storage for your containers. Talk about what's new with EFS and Kubernetes and also what's coming on the roadmap. We're going to be talking about identity of pods and storage and how to bridge between those, how to use EFS from EKS, and some best practices. So let's start with why. Many of the customers that we talk to are in the process of modernizing their applications. They're taking existing applications that are running in servers on premises or EC2 instances, they're containerizing them, and they're moving them into Elastic Kubernetes Service. And when they do that, they're finding that many of these applications currently use storage. So they use storage either to persist data outside of the application or because they're sharing data between multiple instances of an application. And when you're on premises, today you're doing that with a SAN or a NAS or something like that. And when you move into Kubernetes, you still have that need. And Amazon Elastic File System is the solution for meeting that need when you move into containers. Why are these customers modernizing their applications with containers? There's a few reasons. One is to save cost, because when you use containers and EFS, you're able to get much better utilization, not only of your compute, but also of your storage infrastructure. Next, you can increase your agility by scaling your compute and storage along with user demand. And last, by taking advantage of continuous integration, continuous deployment, you're able to move a lot faster as a development team. So let's talk about what kind of applications commonly need persistent file storage. Generally, there's two categories. There's long-running stateful applications that need to save data outside of the container to ensure that if those containers get rescheduled, the data isn't lost because container images are ephemeral by nature. Next, many applications need to share data, either with other applications within the same scale-out group or with other applications. So just some examples of this are developer tools like Jenkins, Jira, and Git all need to persist data to make sure that as containers scale or moved around, the data stays in place and you're able to be effective as a development team. Next, web and content management systems often need to scale up and down with demand, and you need to make sure that your WordPress and your Drupal and your Nginx instances are all working off of the same set of data, so they're all serving the same pages. Next, many data science environments use EFS for a few different use cases. One is because when you're training machine learning models, you're often doing so across multiple container images, you would keep your training data in a shared file system like EFS, so all of those containers can access the same shared training data. Next is data science tools often use EFS. So for example, data science notebooks benefit from having a home directory for each of the data scientists. That makes it easy for the data scientists to bring data in, take data out, share data with other data scientists. And tools like Airflow need to persist data just to keep track of the ETL jobs, interim files, things like that. EFS is commonly used for that. So let's talk about what EFS is. EFS is serverless file storage. It's cloud native, highly reliable, and cost optimized. It's cloud native because it was built in the cloud. So it's a fully managed pay-as-you-go service. And it's integrated with the other cloud services that you might want to use, like Elastic Kubernetes Service. Next, it's highly reliable. EFS is a regional service, which means when you write data to EFS, it's persisted to at least 3 availability zones within that region, and that data is available from all availability zones within that region. Next is it's cost optimized, not only because it's Elastic pay-as-you-go, but also because EFS supports 2 storage classes, EFS Standard and EFS Infrequent Access, which is 92% lower cost. So most customers that use Lifecycle Management are able to get blended storage prices of 8 cents per gigabyte a month or less. Now, when you combine Elastic File System with EKS, there's several benefits that happen because these services work so well together. So one is it's super simple to get started with this. All of the EFS configuration is part of the Kubernetes native objects like persistent volumes. So developers can easily take advantage of this without getting involved with a storage team to provision anything. Next, it's highly available and durable. We just talked about how Amazon EFS is a regional service. Elastic Kubernetes service is also a regional service. So the fact that both of them are regional services means that you don't have to worry about where your containers launch and where your storage is. You get the benefits of high availability and durability just by default with using these services together. Next is elasticity. Both of them have elastic in the name, so that part's kind of obvious, but also because you can scale up and down your storage independently from your compute. So an extreme example of this is if you have an application that only needs to be serving user requests during the day, you can scale it down to 0 overnight, persisting the data to EFS so you don't have to pay for the compute cost if there's no demand for your application. Next is we've integrated these in a way that is secure. We'll talk about how EFS access points can be used with Kubernetes to bridge the identity between containers and storage. Let's talk through just a couple of case studies here. So one is T-Mobile. T-Mobile is using EFS with containers because they wanted to be more agile in meeting their user demand. So before, they weren't able to scale up and down fast enough as demand for their individual services went up and down. So by adopting containers and by allowing their development teams to self-provision EFS and attach those to their containers, they were able to convert many of their applications into containers and microservices and achieve the agility that they wanted to. And in doing so, they were able to get off of their self-managed NFS server and save 70%. Next, Discover Financial moved their data science environment from on-premises into AWS using EKS and EFS. So this is an example of the data science tools using Elastic File System, like I mentioned earlier. So they're using EFS for their home directories, enabling their data scientists to be really effective at just having their own workspace, having their own tools, and sharing data effectively back and forth. And by the way, they saved a lot of cost in doing this and saved a lot of the time they spent managing their existing infrastructure. So now let's talk about what's new with EFS for Kubernetes and some of the things that are coming on the roadmap. So the big news is July 24th, we announced general availability of the CSI driver for EFS. So this is a big milestone for the driver. It means it's fully generally available, not only by AWS standards, we've been supporting the driver for a while now, but also by community standards as well. There's three main capabilities that came as a result of this. First is support for EFS access points. We'll talk about how to use those in just a bit. Another is security is important to everybody, and we wanted to make sure that it was as easy as possible to use security best practices. So now TLS, so encryption of your data in transit, is now enabled by default. So you don't have to specifically configure that in order to get it. And last is we've upgraded the driver to be compatible with the CSI 1.2 spec, so there's additional capabilities that come with that as well. So some of the things that are coming. The big thing that we're looking forward to is adding support for EFS and EKS Fargate. So now not only can you use EFS from EKS containers and pods that you launch on EC2 instances, but also be compatible with pods launched into Fargate as well. Keep an eye on the GitHub number 826 on the container roadmap for any updates on that. We're really excited for it. A couple of other items on the roadmap that we're also looking forward to. One is dynamic provisioning. So the ability to dynamically provision persistent volume claims from EFS access points. So now you don't need to pre-provision persistent volumes in order for developers to use those. Next is EFS now has IAM authorization in the data path. You're able to use IAM to say who's allowed to access a file system and who's not. And EKS has IAM rules associated with service accounts. So one of the things that we're going to be doing is allowing both of those things to work together. So keep an eye on those GitHub features. Comment on them if they're interesting to you or if you have thoughts on how they should work, and look forward to them. Next, let's talk about identity. How to bridge the identity between your Kubernetes pods and your EFS storage. Let's talk through an example. In this case, we're going to be connecting a pod to an existing EFS file system with files and directories already set up. So we see here there's 3 directories. 2 are owned by users and read, write, execute for those users. The other is owned by a group and can be read, written, and executed from that group. And the pod that we're connecting has a container where that container was built to run the application as root. So what we see is when that container connects to the file system and tries to access Bob's directory, it succeeds. And the reason it succeeds is because the identity is taken from the container build time of root. So root can do anything on the file system, including reading Bob's directory. So the key thing to keep in mind is by default, POSIX identity comes from the build time of the container. So how you configured the application to run when you built it rather than anything about the runtime of that container. So let's talk about how to deal with that. EFS has a capability called EFS access points. Let's look at how you define an access point. Of course, it has a name. You associate it with the file system. But the key thing here is your access point has what's called a POSIX user. POSIX user has a user ID, group ID, and secondary group IDs. When you use an access point, all applications that connect through that access point are going to inherit this user ID and group ID, not the user ID and group ID the container was built as. So this is an override for the identity of your container. The other thing that access points can do is place your application in a specific directory. So here we've configured apps/myapp as the directory, and we're having EFS create that directory for you with a set of privileges of user group ID, user ID of 1, 2, 3. So we're matching the ownership of the directory to the user that's coming through. So the way we've configured this access point makes it so that any application that comes through gets a specific user ID and group ID of 1, 2, 3, and we place them into a directory that we know that user has read and write access to. So there's 2 key things, 2 key benefits of using access points. One is it enforces file system identity so that your root containers can't escalate their access, and arbitrary users that are built in containers, let's say you built your container with user ID 16482, it's not locked out of whatever it's trying to access. Next is it does you the favor of creating application-specific directories with permissions. So now you don't need to spin up EC2 instances or having any side processes to manage your directory structure in your file system. You can do all of that just from EFS APIs and CloudFormation and things like that. So looking at how access points work. So like I mentioned, when you have an application that connects to an access point, the identity is overridden by the access point identity. So here we have our same application that is reading and writing as root because that's how the container was built. When it passes through the access point, all of those accesses are rewritten as the user ID and group ID of the access point itself. So we're translating between 0 and 1, 2, 3. So now the user ID and group ID are meaningful on the file system. And they give the application just the right access for what you want at runtime. So there's a couple of different use cases for access points. So one is everything that I'm just mentioning. So solving the container identity issue of bridging between your Kubernetes pods and EFS file systems. Another reason you might want to use access points is simply because you want to share file systems between multiple applications. So you might want to do that because you just want to create less file systems, have less file systems to monitor in your CloudWatch metrics and things like that. Another reason is if you want to share throughput with multiple applications. We'll talk about how throughput works in a second, but in bursting mode, the throughput of your file system is based on the amount of data that you have stored. So if you combine applications, you can get an aggregate throughput based on all of the data that you have and then borrow between your applications as needed. So depending on what kind of applications you have, that might be a good idea. Next, let's talk about how to get started using EFS with EKS using the CSI driver. Let's start with some concepts. So CSI is the interface. So it's a standards-based interface that makes it possible for lots of storage providers to integrate and look and feel the same so that developers don't have to worry about the details of any specific type of storage. EFS CSI driver is the implementation of EFS for that framework. And then there are several standard interfaces that administrators and developers work with. So there's the storage class, persistent volume, and persistent volume claim. Best way to explain those is in the next slide, which is the visual representation. So if you have a big Kubernetes cluster, it's possible that you have multiple types of people interacting with it. You have an administrator type who is setting up all of the resources that developers can use, and then the developers themselves, which are launching their applications. So the administrator would set up the storage class, which is just a name for a type of storage provided by Kubernetes. So in this case, I named it general purpose EFS. And within that storage class, you build a pool of storage resources called persistent volumes. So here I've created a few file systems and configured a few access points within those file systems, and from those created my pool of persistent volumes. So once you create the persistent volume, they're just sitting there waiting to be allocated by a developer who would come along and they would create a persistent volume claim where they say, I want a unit of storage from the class of general purpose EFS. And the Kubernetes storage scheduler is going to find a available persistent volume from the pool and assign it to that persistent volume claim. And once the persistent volume claim is created, you can allocate it to an application by referencing it in your pod spec. Let's look at how you actually configure these things. It's really simple. So with your storage class, really the only thing you have to do is reference the CSI driver in the provisioner field that we highlight. Next, when you configure your persistent volume, what you do is you reference the storage class, and then you say which driver it uses, and then you use the volume handle. We'll talk about how to configure your volume handle in just a second, but basically that's how you reference your specific file system and access point configuration. You can ignore a lot of the other fields. So one of the things that you see in here is storage of 5 gigs. Because EFS is a fully elastic file system, this field is ignored. We'll give you any of the persistent volumes knowing that it can grow as big as you need it to. So you don't have to worry about finding a persistent volume of a specific size based on your app. You can use any of them and then grow into it. So there's a new thing with the GA version of the CSI driver, which is we've extended volume handle in order to let you reference not only the file system ID, but also the subpath of that file system and the access point ID of that file system. Generally, you'll use either subpath ID or access point ID, but there are maybe cases where you'd use both. So some examples of volume handles for these. So if you want to mount a subpath of a file system, you would use the file system ID colon the path within that file system, and then just another colon after that in blank. If you wanted to use an access point with the file system, you would reference the file system ID, colon, colon, and then the access point ID. And of course, you can use all three in the last example. So the reason that we are packing all of this into the volume handle was we want to make sure that the Kubernetes scheduler sees each one of these as an independent persistent volume. If we didn't have all of these in the same volume handle, Kubernetes may get confused and think that you're trying to over-allocate the same file system resource multiple times. So once you've created your persistent volume and you've configured your volume handle, your developer can now create the persistent volume claim and launch the pod. So in that case, the persistent volume claim really is as simple as storage class name and Here again, the actual amount of storage is ignored because of the elasticity. So all the developer really has to know is, I want some storage of type EFS storage class, and the Kubernetes scheduler would take care of it. And then you launch your pod simply by referencing that persistent volume claim and saying where specifically you want it mounted into your pod. And then you're done. So now let's talk through some best practices for performance, cost, and how to get your data in. So first, to catch you up on the latest performance announcements that we've made, because we've been really busy improving EFS performance, we've, in April, increased the number of IOPS you can do on a general purpose file system by 400%, from 7,000 IOPS to 35,000 read IOPS. And then on July 23rd, we improved the performance of individual NFS connections. So this is the performance that you can expect from a single mount or a single instance of a pod. We doubled the throughput from 250 megabytes per second to 500 megabytes per second. So general advice for performance: first, use general purpose file systems for most apps. It has a lower metadata latency, which means all of the individual file operations will be faster. You may want to use max IO file systems if your workload is highly scale out in terms of number of concurrent pods, and if they're all working on a different set of data within your file system. You may get better performance with max IO for that one. Next, configure provision throughput to start out your file system. So the way that throughput works with EFS file systems is we calculate your allowed throughput based on how much data that you have stored. So if you have a brand new app that's starting out that hasn't put much data in yet, you may not have the throughput that your application needs. So in that case, you simply configure provision throughput and tell EFS exactly how much throughput your app needs. And then as your application storage grows, eventually if it grows to the point where you'd be entitled to more throughput than you configured, we'll give you the bigger of the two. Next, set up Amazon CloudWatch in order to monitor your throughput, your IOPS, and make sure that everything is within the range of your file system. We have a GitHub page with a template for a pre-configured dashboard with alarms and stuff like that to make it really easy to get started monitoring the right way. Oftentimes, customers ask, should I use EBS or EFS for a particular use case? The reasons where you would definitely want to use EFS are twofold. One is if you need to share data. So if you need to share data between containers, then you need a shared file system, which by definition EFS is. The other reason is EFS is a regional service. So if you want to share data between instances in multiple AZs or be able to move an application from one AZ to another, then EFS is the service that can help you do that because your data is available from all AZs within a region. One example you might want to do that is to take advantage of spot pricing, for instance. On the other hand, you may want to use EBS if you need super low latency for for instance, a relational database like MySQL, or if you want consistent point-in-time snapshots across multiple files within your volume. Another option also is FSX for Lustre. So FSX for Lustre is a file system that's optimized for job-based compute workloads like high-performance computing, simulation, stuff like that. It scales to hundreds of gigabytes per second of throughput. Next, make sure you're optimizing your costs by enabling lifecycle management on your file system. With lifecycle management, you can save up to 92% on the data that you aren't frequently accessing. So often you can get blended storage prices of 8 cents per gigabyte a month or less. So it's just a checkbox to turn on, and all customers that turn it on have gotten cost savings. Next, make sure you're configuring backups. So backup also is super simple to configure. You create a backup plan of how often you want to back up your file system, how long you want to save those backups for, and the system just takes care of it within the AWS backup service. And the benefit here is if you have an application that runs away and accidentally deletes some data or something like that, AWS backup will let you recover it. You can either recover a whole file system or a individual item like a directory or a file. So it's a great insurance policy to have on for your application data. Next, Now that you're looking to migrate application into an EFS file system for an app modernization from on-premises, the best service to use for that is AWS Data Sync. AWS Data Sync can take data from on-premises SAN and NAS and move them into EFS, and it's a fully managed service. It can do it one time, it can do it incrementally, making it really easy to move your data into the cloud. So that's what I got for you guys today. Thanks for attending. Where to learn more. So a great place to get started is just to take a look at the EKS documentation for the CSI driver. It's been updated for all the new GA capabilities. We also have a new blog out for how to deploy Jenkins using EKS and EFS. It also uses access points. So if you're curious how to get started with that, you can look at that blog as well. Thanks for your time today.